I'll hit play. So chapter 4, I guess chapter 4 starts with this definition, and what's kind of funny is in 3 weeks, when we take our test in 3 weeks, I think the very first question is this. You might forget that 3 weeks from now, but try not to. It's the definition. This is a definition of what we call a critical number. We've already sort of been messing around with critical numbers, except I don't think I ever called them that. Let me show you what the definition says. It says if f of c is defined, okay, f of c is defined, then x equals c is called a critical number. That's the definition. It's called a critical number. That number, x equals c, is called a critical number if blank or blank. So this is usually how I put it on a test. Now, again, 3 weeks from now, you should be able to fill in those blanks. Today, I'll fill them in for you, I guess. But you know what we've been doing? We've been taking derivatives, and often I've been asking you, hey, when does that derivative equal 0? That's been or when do we have a horizontal tangent line, which is when the derivative equals 0. We learned that in chapter 3, but it's definitely going to sink home now in chapter 4, because that's what a critical number is, when the derivative is 0, or, so I'm going to write that. Now, how do I write that? F prime of c equals 0. So in other words, the derivative at this point, we're talking about this point x equals c being a critical number. It's some x value apparently, but if it makes the derivative 0, that's what makes it a critical number. Or if it makes the derivative undefined. And again, from chapter 3, we were kind of hitting these ideas. These were places of horizontal tangent lines. These were places of non-differentiability, right? But both of those places are kind of important points. We call them critical points. Actually, when I just refer to the x value, I guess the x value I call a critical number. If I did use the word critical point, what do you think I mean? If I use the word point, then I think I want an x and a y, right? I want an x and a y value. But sometimes we're just looking for the x values. Yeah, here, let's just see if we can find any critical numbers. Watch this. Okay, here's a function. Here's a function 2x times the square root of x plus 4. I think we can find some critical numbers. How do I find critical numbers? I take the derivative and pay attention to what this definition says. Right. I guess I should take a derivative and ask myself these two questions. When is it 0? When is it undefined? Yep. So I get to practice more derivatives through chapter 4, in case chapter 3 didn't serve you well enough. Chapter 4 can help you. I'm going to do this derivative. It's one of these product rules again. Some of you weren't really catching this on the test. It's a product rule. Most people, you should have got it by now, but some people were messing this up. It's a product rule. Here we go. The derivative of the first, 2, times the second, plus, write down the first, and take the derivative of the second. The derivative of the second thing is 1/2 x plus 4 to the negative 1/2. The chain rule says you should do the derivative inside there, which is a 1. Thank you. Not much of the chain rule there. And so we're finished. We're finished. But now, maybe now, because of this thing that we're looking for critical numbers, maybe now you really see the value in cleaning this up. I mean, the question now is, when is this 0 and when is it undefined? right? When is the derivative 0 and when is it undefined? That's my question, to find critical numbers. Anyway, you know, you need this cleaned up. You need this simplified in order to answer those questions. So we spend a lot of time simplifying, and we need that now. Maybe now you see why. Let's see, if I try to clean this up, I think I'll factor. I like to do it by factoring. Some of you, again, started to grade your tests, and you were doing some moves here, and there's different ways of simplifying. You don't have to do it my way, but I did try to teach you this factoring move. You factor out the x plus 4 to the negative 1/2, and you're left with a 2 times x plus 4 to the first. Do you guys agree with that? I pulled out an x plus 4 to the negative 1/2. That's the game I was trying to teach you last week. What's left over here? Over here, this is factored out, and I'm just left with 1/2 times 2, just a good old 1x, I guess. You know, if I clean this up, I distribute. It's a 2x plus an 8 plus another x. So there's a 3x plus 8. I'm going to leave that in the numerator, drop him into the denominator, and I'm done. You know, this is my derivative. So, you guys okay? Yeah, that's old stuff. As of last week, it's old stuff, or last chapter. Question?
You think you just leave it as 1/2 instead of the square root?
That's true. I mean, I cleaned it up. I didn't have to call this a square root. Leaving it as to the 1/2 power is okay with me. Right, it's a negative 1/2 in the numerator. You move it down, it would be a positive 1/2. Right. It's okay. So here I go. Now I want critical numbers. Again, this is the new thing. We're looking for critical numbers. This is a big theme for the whole chapter, really. We are sitting here at 4.1 with this definition, but I'm looking for critical numbers. So when does this derivative equal 0? We talked about that. You know, the algebra involved here is that this equals 0 when the numerator equals 0. And so it's really about just setting the numerator equal to 0. Moving the 8 over, divided by 3, I guess x is negative 8/3. Right, you guys? And when is it undefined? Look at that guy. When is he undefined? I'm looking for both these places. When is the derivative 0? When is the derivative undefined? Can you tell? I guess it's undefined when the denominator is 0. Do you know when that is?
X equals -4.
When x is -4. Thank you. Can you see how do you get a 0 in that denominator when x is -4? Yep. Yeah, good. These are two critical numbers. These are my critical numbers. They're kind of different kinds of critical numbers. One of them makes my derivative 0. The other one makes my derivative undefined. I mean, they're both critical numbers, but they come from the two aspects of this definition. Wait a minute. Maybe I should hang on a second. You know, to be an official critical number, you got to have this. But there was a first sentence up here. What was the first sentence? Oh. That c has to be defined in the original function. To officially be a critical number, it does have to be defined in the original function. So we don't count holes or discontinuities, I mean, if it's not a point on the original function, it's not a critical number. I mean, if it's an asymptote in the original, we don't call that a critical number. So let's see. Are these defined in the original function? I mean, if you plugged a -4 back in, is this okay to have a -4 in this square root?
Yeah.
You get a 0. There's nothing wrong with a 0, right? What would be bad? You can't have a square root of a negative number. In fact, so that makes me, maybe I should think about the domain of this original function. I haven't thought about that in a while, but it's not too difficult. Let's think about that. What is his domain? What x values am I allowed to plug into this function?
-4 and up.
I think you're right. I mean, because of this square root, I mean, a lot of times your domain is all real numbers, you know, there's no problems. But he's right, with this square root, I can't let the argument of the square root or what's inside the square root be negative. So you're kind of saying that the x plus 4 better be greater than or equal to 0. Is that what we're saying? I want what's inside the square root to be positive. So move the 4 over. You're saying x better be greater than or equal to negative 4. All right, does this meet that category? Greater than or equal to negative 4?
Yep.
Yeah, okay, cool. He's a critical number. What about this? Is this greater than or equal to negative 4? I gotta check my number line. I think it is, isn't it? Negative 4 is, we're saying the domain is all these numbers. That negative 8/3 is negative 2 2/3. Yeah, that falls in here. Yeah, these are both critical numbers. It's funny, one of them's, you know, a good critical number here, negative 8/3. The other one is kind of right here. It's an endpoint. You know what I mean? It's an endpoint. Oh yeah. Remember, this critical number made my derivative 0, right? And the other one made my derivative undefined, which means it's a point of non-differentiability, and that can happen at a sharp point or an endpoint. I think this time it's an endpoint. It's just because I analyzed the domain and realized it's an endpoint. But it's still a critical number. Critical number. These are critical numbers. Hey, why are we looking for critical numbers? I'm going to get rid of this question too, by the way. Are you guys okay? I don't want to do anything else with it. I'm going to get rid of it. Let's do this. Here's a visual. Look for find some critical numbers for me. Watch this. This is a visual. There's an x-axis and a y-axis, and here's a picture of a function. All right, here's a picture of a function. Do you see any critical numbers? Visually, can you just see critical numbers? Here they are again. I mean, there are places where the derivative is 0 or where the derivative is undefined. I mean, that's the definition. Again, so can you see them? I mean, you know when the derivative is 0, we've kind of hit that topic. Those are horizontal tangent lines. And do you see where that happens? Horizontal tangent lines happens here. Yeah, there you go. There's a critical number. That's a place where the derivative is 0, right? The derivative is the slope of the tangent line. The derivative is 0 there. Where else? Right up here is a critical number. I mean, these are the x values. Yeah, you're right. And this place, this is where the derivative is undefined. I think that place where the derivative is undefined. Yep. That's not a horizontal tangent line, but it's a sharp point, and that just caught my eye. I remember a sharp point is one of these places. So cool. I got 2 of those and 1 of those. I got 3 critical numbers I can just see visually. I didn't go do the math and find them. I don't have a function. I didn't do a derivative, but I'm understanding this. Good job. Yes, Carlos?
Does C really mean anything, or is that what critical? Is it symbol for critical numbers?
Well, it's just a number. It's x equals C is some place. I mean, sure, it can stand for critical number if you want, but it's just a number. Okay. Hey, so maybe this visual will also help you come up with this conclusion. I mean, why are critical numbers so important? What's happening at critical numbers? I mean, there's a lot of ways to say it. Oh, you have horizontal tangent lines. Oh, you might have sharp points. You might have end points. But I'm looking for some other words here. I think you already said it. Looking at this picture, critical numbers happen when you have Mins and maxes. Yeah, you're right. Mins and maxes. Minimums and maximums. And we use the word relative minimums and maximums. This point right here is, I'm going to call it a minimum. And I'm going to call it a relative minimum. And what that means is he may not be the ultimate minimum. When we look for mins and maxes, we're not looking for ultimate max or ultimate min. Well, we might if the question asked me for that. Usually I'm not interested in that. I'm just looking for little local or relative maximums and mins, which means this. Relative to his little neighborhood, he's kind of the low guy of the neighborhood. Sorry about that. Poor guy. I mean, he's the minimum. He's a local minimum, local to his little region around him, in a little neighborhood around him. What's funny is I use that word neighborhood, and you haven't heard it much, but it is a mathematical term. It's an interval around some point. We do use the word neighborhood, a little area, a little interval around some point. So around this little point, he's a local or relative minimum, and around his little. And he might not be the ultimate max, but he's a relative max. Relative maximum. And this guy here is a minimum. I just call him, he is a minimum. I'm not calling him the minimum. I'm saying he's a minimum. But technically, I should probably say relative minimum. Are you guys okay? You know, one thing that happens with a new chapter or new topic is some new language, new terminology. I've used the word ultimate max or ultimate min. Technically, the technical word is absolute. When I use the word absolute max or absolute min, then I am interested in the winner. I mean, you might have a bunch of maxes, a bunch of little maxes, but who's the ultimate max? I said it again. I said it wrong. I mean, who's the absolute max? Do we have one? I mean, actually, we only have one candidate for maximum. There he is. And would you call him the absolute max? Actually, no. Because this graph keeps going up, you see, I mean, and maybe I misled you, but it does. It keeps going up forever. So guess what? And by the way, this goes up forever too. Looks like it's slanted here kind of, but it goes up forever. Anyway, if those ends go up forever, there is no absolute max. Okay? There is no absolute max. Is there an absolute min? Well, there's a couple of relative minimums. Is one of them the ultimate lowest min? It would be this one. And so we could, right now, it's okay to call him a relative min, and that's a relative min. But ultimately, we would end up also classifying him as the absolute min. Are you okay? This is a relative max. This is relative min. This is a relative min. This is a relative max. But then if I use the word absolute, then he is the absolute minimum. Listen, there's some questions about that. We should be able to understand that. The truth is, we're mostly looking for mins and maxes. And when I say that, I mean relative mins and maxes. I don't care a whole lot about who's the ultimate, who's the absolute min and max. But the book might ask, we should know the language. There's a lot going on. Finding a min or max doesn't seem all that hard. It's a high point, a low point, a high point, a low point. There's a lot of what's happening in between those high points and low points is kind of interesting at times. If you read this thing left to right, can you say increasing or decreasing? Can you talk like that for me a second? Reading left to right, what would you say is happening kind of over here? decreasing. If reading left to right, the function is falling until it hits a minimum, I guess. So for this whole kind of region right here, we would say it's decreasing. Good. But once it hits its minimum, it hits a minimum. What's it do? I mean, it's almost the definition of a minimum, right? You got to decrease, you hit a minimum, and then you have to increase. I mean, if you kept decreasing, I don't think it would be a minimum, would it? Right. You got to decrease, hit your minimum, then you got to turn around and increase. So sometimes they call these turning points. You're turning around. So you're decreasing, and then from here to this max, in between this little area right here, are you guys with me? You are increasing. And then you hit a max. And then by definition, you're not going to be a max if you keep increasing. You got to turn around and start decreasing again. Are you with me? So now it's decreasing. Where's it decreasing? From here to here. It's decreasing. This picture's getting messy, but maybe you're getting the point. It hits a min, and then what does it do? Then it increases, right? So the rest of the way, from left to right, the rest of this way, it's increasing. All right, we're learning. This is a big theme of this chapter, and I'm diving right in. With this discussion, I'm sort of easing into 4.3. That's what I do. I'm in 4.1, I'm 4.3. I'm sort of skipping 4.2 for right now. So just keep that in mind when you try some homework. In fact, my homework might completely skip 4.2, but there might be some stuff in 4.2 I need to revisit. I might get back to it. So, but for now, we won't worry about 4.2. 4.1 introduces us to the idea of critical numbers. And when I start talking about decreasing and increasing and mins and maxes, I'm sort of getting into 4.3 a little bit. So, yes, Carlos?
Does this mean we're not going to be working in 3.8 at all?
Oh, no, we might do that eventually. And like I said, this picture's getting messy. There's more stuff I'd like to say. I'll tell you what, let's just do this. Here's a simpler example. So tell me what this guy's doing. Decreasing, increasing, can you tell me? Decreasing until it hits a minimum, and then it increases. Okay, thank you. Decreases, left to right again. Decreases, hits a minimum, then increases. Okay. Yes, Carlos?
I noticed you said what's the right. Is it ever going to be the other way around?
No, we need to all agree to read left to right. That's a good question. We don't ever want to read right to left, because then we're backwards, right? I mean, just try it for a second. If you want to read right to left, you would say it's decreasing, it hits a min, and then it increases. I mean, but I don't want you to call this decreasing. I don't want you to read right to left. I want you to so we all read left to right, then we can, because if we all read left to right, then we can agree that this side is decreasing. We hit a min, then we increase. But here's the thing about, so what did we just say? Hang on, watch this. Over here, we said the function is decreasing. Is that what we're saying? The function is decreasing. Okay. And if we drew a tangent line over here, and there's a tangent line, there's a tangent line, there's a tangent line, if I think about the slope of these tangent lines, what we've thought about so far is the slope of this tangent line. What's the slope of this tangent line? 0. But what about the slope of this? I'm going to make a little note here. F prime equals 0 right here, right? Is that okay with you? The derivative is 0. The slope is 0 right there. But what about over here? What's the derivative doing? The tangent line is, the function is decreasing. The tangent line is decreasing. What does that say about a slope? Well, the slope might not be decreasing, but if if you draw a line that's decreasing, his slope is negative. Took me a while to get that out, but you guys know that. When a line is slanting this way, his slope is negative. When a line is slanting this way, his slope is positive. In between there, it might be slanting this way, which is a slope of 0. So hang on, what did we just learn? The function is decreasing. The tangent lines look like they have a negative slope. If the tangent lines have a negative slope, then we're saying the derivative is negative. Is that okay with you? Then the derivative is 0, and then over on the other side, you would look at that function and you would say, oh yeah, man, that function is increasing. That's what you would say. The function is increasing. But what's the derivative doing? The derivative, I don't want to say whether he's increasing or not. The derivative tangent line the derivative is the slope of this tangent line. And I would just say because it's slanting that way, it is positive. That's all I want to say. The derivative is greater than 0 or positive. Hey, this means this. This means this. This means this. This goes together. And this goes together. And that's a new idea, I think. Although it's real logical. I could have told you this idea a long time ago. You see how logical it is? When a function is decreasing, his derivative is negative. I mean, I hope I've convinced you, but it needs to become part of your soul for chapter 4. Just for chapter 4. When the derivative, not really. It's a huge calculus idea. When the function is decreasing, the derivative is negative. This is how the derivative helps us learn about a function. When the function is increasing, the derivative is positive, or vice versa. If the derivative is positive, the function is increasing. I mean, these thoughts go together. These are concepts we need. And by the way, if you're decreasing and then increasing, in between decreasing and increasing, you must have hit a slope of 0, and would it be a min or a max? It would be a min. If you're, wait a minute. If you're decreasing and then increasing, you must have hit a min. If you're increasing and then decreasing, you must have hit a max. Again, reading left to right. Okay, this is awesome. These are all concepts and ideas. You're learning. You're digesting them. We should work on some problems. Let's do this problem. F of x is, hold on, don't look. All right, good luck. That's a function. Here's what I'd like you to do. Find the critical numbers. Find the critical numbers. I'm going to be right back. I'm going to hit pause on this a second.